And Samuel is going to present
Excellent.
this work. Let's give him a big clap.
Okay, so thanks for the introduction. So this is joint work with me and my supervisors, Parosh and Bengt, and the two people from IIT Bombay, Krishna and Om. So I'm going to remove my mouse cursor because that's going to irritate me. Okay. So you have a concurrent system, and oftentimes they communicate through some shared object. And this shared object is, for instance, a stack or a queue or something like that. And this, to reason about the correctness of such a system, we need a correctness condition that's hopefully composable and that captures this interacting with a common object. And once the standard such correctness condition is linearizability. And linearizability is a way to extend a sequential specification, like the ones for stacks or queues, for instance, to a specification in the concurrent setting. And it does so by taking an execution. So this is an execution. We have operations that are these pushes and pops, and we have their calls is the left point of these lines, and the returns are the right points. So linearizability says, well, this history is considered linearizable if we can pick a time point in each of these operations, or alternative, extend the partial order, the happens before order, into a total order, such that this now sequential history corresponds to the definition of, or to the specification of the original sequential structure. So this is a stack execution, so the original history was linearizable. And we are specifically looking at the monitoring problem, which is when we take an execution like this and ask, is this linearizable? We're not looking at implementations. So we just expect a sequence of calls and returns to these operations. And unfortunately, this is NP-complete in the most general case, and even for simple structures such as registers. So we have to make some additional assumptions. And a common such assumption is that the histories are differentiated. And this means that each value just occurs in, at most, one adding operation, so a push, and removing operations, a pop. And in fact, this is a very sound assumption, because it turns out that for implementations, if you have an implementation that implements a stack, it is correct, like it's linearizable, all its executions are linearizable, if and only if all of its differentiated executions are linearizable. So it suffices to just look at this. So, and the second, well, rather, this is a non-differentiated history. And the reason that we can do this is that this history, this non-differentiated history, is linearizable if and only if there is some differentiated history that we can obtain by just renaming it, or rather we can obtain the original history by renaming the values of this differentiated history. Okay, but this is a tricky problem, apparently, because this is linearizable. We just saw that on the first slide, but this is not. We only swapped the order of two events. So it's not always easy to see whether it's linearizable or not. And in fact, this has shown in previous work. So we have, in our paper, we have found errors in previous work. Notably, this is a quite recent paper on this that produced a quadratic time algorithm for monitoring stacks, which is incorrect. It does not differentiate between the two histories on the previous slides. And there was an attempt earlier in 2018 for an algorithm for something that is more general for a class of structures, which also was incorrect because you found a bug in the proof. The algorithm we don't know, but the proof was not correct. So we'll present our algorithms that we have proven are correct. And for stacks, it's quadratic in the length of the history. And we do this by computing what we refer to as populated and deserted segments of this of the stack history. And then we apply some simplification steps, which is either we remove extreme values or we partition it. I'll get to this. And if we ever cannot progress, we conclude that it's not linearizable. Okay. So the first thing is that we can ignore the threads. So Here we have 3 threads that are performing operations, but the specification itself says nothing about the threads. It just cares about when things call and return. So we're just going to draw it slightly differently and just put the values side by side. Okay, so the first thing we do is we compute what we refer to as the cover. So between the return of the push for any value and the call of the pop for that value, we know that that value must be in the stack. Okay? So what does that mean for when we take the union of these? Well, that means that in this yellow, which we call the populated segment, which is the union of these covers, there must be at least one value in the stack. Okay? And in these green regions on the sides, we know that the stack may be empty, because everything that's already been pushed has also had its pop called. Okay? So what do? Well, we start by finding extremes. So we see here that the push to B intersects the leftmost deserted segment, and the pop to B intersects the rightmost deserted segment. So we can just put B at the ends. Push B first and pop B last, okay? And then we start again. We compute the cover, we compute the populated and deserted segments, and this time there's no extreme value. So what we do instead is that we see here that in this middle, we have an inner deserted segment. And this means that there is some values whose pushes happen before this, the populated segment to the left of it, and whose pops are called at least here at the start of this deserted segment. And similarly, there is a populated segment here, so that we know there must be something to the right. So what we do is we just separate the history here. We say that, okay, well, we do whatever we want to do with the left side, which is A, and then we do whatever we want to do with the right side, which is C and D. Okay. So we look at the left first. Well, we do the same thing. This is maybe a bit easier example, but because we can just, it's extreme, we put it like this. And then we move on to the right side. We find the cover, we find the populated and deserted segments, we find that they are extreme, and we put them like this. We have found the linearization, hooray, the history was linearizable. Great. Well, we made some additional assumption. The first is that we assume that every history is completed, like every push has a matching pop. But if there are some pushes that do not have matching pops, we can just add concurrent pops at the end for those values, because we know that they will be in the stack at the end, because they're not removed. And the second thing is that pop operations might return, well, nothing, indicating that the stack is empty. And in such a case, we can just start like this. We can compute these again. And all of these that intersect a deserted segment, we can just remove them, because we know that the stack can be empty there, so remove it. Well, we still have one left, so this is not linearizable. Okay. Well, and the complexity, just to go through it, it's we sort the values, we compute the deserted and the populated segments in linear time, we find the extreme. In linear time, we partition in linear time, and then in the worst case, each of these steps that we perform just removes one value. So n steps, computation, n squared. So, Qs. Here we do a bit better, we do n log n, and we do this by exploiting a small model property, which is that a differentiated and completed Q history is linearizable if and only if, for no values A and B, we have that A is enqueued before B and B is dequeued before A. So we can just look at what we call critical pairs. So, yeah. And it is important to note that this does not hold for stacks. We can not use any property like this for stacks. In fact, in our paper, we show that we have a construction for a counterexample to there being a small modular property of size n for any natural number n. Okay, so what do? Or rather, this we look at this small modular property expression here, and we compare this to these lines. So what does it mean? Well, it means just that the entirety of the operations for B, from its push call to its, or enqueue call to its dequeue return, is contained within the inner, or the cover interval for some other value A. Okay, so we just need to check containment for these intervals, and that we can do by constructing a tree. So we're going to construct what we refer to as a Q tree, and then scan it for the containments. So the Q tree is a red-black tree that contains a left and right subtree. It contains left and right endpoints for the inner interval, so it contains the inner interval for every value. And then it contains a high key just to help, which is the highest right endpoint occurring in its subtrees, just to help us do the search without branching. Okay, so here's a big history. These are its inner segments. So here we have, for the value 0, we have its NQ returns at 3, its DQ starts at 6, so we have the inner segment 3 to 6. Okay, and the outer segments for 0, the NQ starts at 1, the DQ ends at 8, so the outer is 1 to 8. Okay, so we're just going to go through one of these containment checks. So we're going to ask if this outer segment, 1523, is contained in something else. So we start at the top. Well, 15 is less than 16, so we should probably go left. Okay, here we see that, okay, it's not contained in this interval. 15 to 23 is not contained in 9 to 14, okay. So we look to the left first and see that the high key in the left subtree is not big enough to contain wherever we go here, this high key is going to be too small. So we just proceed to the right instead and find this interval, and we have containment, so the history was not linearizable. And again, go through the complexity. Constructing the tree is n log n. Each search is log n, and we do n searches, so it's n log n. Okay, and finally, the simplest of the three is a multiset algorithm. This is in linear time, and we do this by simply first stating that a multiset history, or set history, is linearizable if every single valued projection is linearizable. So if we can just look at one value at a time, and essentially arrive counters. And then one of these single valued histories is linearizable if and only if the number of returned removes never exceeds the number of called adds. So we can just count, and we're done. Okay? And then there are some other operations you might want to be able to do on sets, for instance, containment checks, main membership queries, and we present in the paper we have a greedy algorithm for handling those. So, in conclusion, we have some monitoring algorithms for stacks, queues, and sets. And we have found issues in previous work, and yeah, we have shown that these are correct. So, for future work, I want to formalize this in a theorem prover. It's sort of work in progress on the side, just to be absolutely sure there is no mistake anywhere. And then to extend this to other structures, such as snapshots or other concurrent objects. And then finally extend it to related correctness conditions. For instance, durable linearizability. There is also k-linearizability and other similar properties. Okay, and thanks for listening. And I am finishing up my PhD and I'm looking for work. Hello, come talk to me.
Any questions?
So can you go back to the multisets?
Yeah, sure. You can try. Yeah.
So over here, the number of return remove never exceed the number of called add. Even if this condition is true, it may so happen that you have more removes before the adds.
Yes, so this was for, wait. No, you cannot have more removes than adds even you have this.
So when you say multiset, it means the same value can be entered many times?
Yes, but if you remove, you remove one
and
of
it
them.
is, oh, sorry?
Yes, if you remove one of them.
And then can I remove again if I had
yes.
two?
So
okay.
if you add, remove is valid.
So, okay, what if the history is such that the first three are remove and then I see an add and they're all ordered like this, remove, add. The numbers will be the same, but then it would
No,
be...
but you look at each, maybe this could have been more clear. So you look at each time point, the number that of returned removes and the complete and called adds. Okay,
so for
before
each prefix.
That. Yes, for each
and
prefix.
how do you talk about a prefix in a history? It's a partial order, so...
Yeah, I mean, we can just, well, the events are in total order. So each push, each call and return, these events form a total order.
Okay.
So we can just go through the events and count.
So when do I count a remove operation to be there? At the call time or at the return?
Return time.
I see. Okay. And can you go back to the queue?
Sure.
So over here.
Where?
Yeah. So next slide.
Next slide.
So over here, the time complexity is n log n, and it is not just coming from the initial sorting of the.
No, I mean, constructing the tree is n log n, and that's just one thing, and then it's plus this, where we do n searches, each is log n.
Okay, thank you. And one last question. So,
yes.
For stacks and queues, and even for multisets, I think, would you be able to carry out this exercise if you had peak operations?
So I do not know if these algorithms are very compatible with peak operations. Because, so right now so peak operations basically can act sort of like a similar as a pop operation in that it constrains it in the same way, that this actually has to be here now. But we would need to do some additional reasoning for that, and I don't know how to do that, at least not by extending these algorithms.
Thank you.
One more question.
Hi, so this is a bit of a tricky question, but since you did mention, so you mentioned that you have found some faults in the proofs of previous works.
Mm-hmm.
How confident are you in your current proofs?
I am fairly confident. I've written them and then done them again, and then had 2 or 3 people double check them. So I'm fairly certain.
Okay. And can you mention what's the actual bug you found in the previous proofs?
Okay, so well, the bug in a proof we found was, let's see if I remember the correct terminology. They presented a hornification procedure for what they called operation order specifications. And it turns out that this hornification procedure was not sound. And their proof for its soundness was incorrect.
Thank you.
Okay. One very short additional question.
Thank you. Eris Petrang from Technion. So when you say monitoring, do you mean that you go step by step, and when it's not linearizable, you shout, "This is not linearizable"? Okay. So did you try to look at not strong linearizable things where you simply don't know at the point?
So that's part of the future work, right? Related conditions. No, snapshots is one line of work, right? Other structures, but then also other correctness conditions. So non-strong, weaker forms of linearizability.
Yeah, it's still linearizability. It just doesn't have an extra strong property. Maybe. I mean, there's a paper on strong linearizability.
Okay.
And there is a difference if you, at the end of the execution, you look for an order, or you know at any point if things have been linearized or not.
Okay. Yeah. Okay.
So,
okay. Yeah. Okay.
And some snapshots are not like that.
No.
You cannot.
I'm not sure that even stacks are either.
No. These are strongly whatever you gave is strongly linearizable.
Okay.
Sorry, probably should wrap up here because time is a little bit over. So let's thank the speaker again.